Assalamu alaikum. This is lecture 29 of data security and encryption, and in this lecture we're going to discuss about the transport level security. Virtually all businesses, most government agencies and many individuals now have websites. The number of individuals and companies with internet access is expanding rapidly, and all of these have graphical web browsers. As a result, businesses are enthusiastic about setting up facilities on the web for electronic commerce. But the reality is that the internet and the web are extremely vulnerable to the compromises of various sorts. As businesses wake up to this reality, the demand of secure web services grows. So the topic of web security is broad and one can easily fill up this entire course. However, in this lecture we are going to discuss some of web security consideration along with the web security threats and web traffic security approaches. Our transport layer security protocol will be discussed along with this architecture, record protocol, cipher specification protocol, and its cryptographic computation. And finally, a heartbreak protocol along with some SSL TLS attacks will be discussed. The next famous protocol in discussion is the hypertext transmission protocol over the SSL layer, and its connection related properties will be discussed. And finally, some discussion about the secure shell protocol along with the transport layer protocol and user authentication protocol will be discussed in the connection oriented uh, way. As described earlier, web security is a broad topic, and the World Wide Web is fundamentally a client-server application running over the Internet and the TCP/IP intranets. The following characteristics of a web usage suggest the need of a tailored security tool. Web servers are relatively easy to configure and manage these days than in the past. Web content is increasingly easy to develop, and the underlying software is extraordinarily complex, which may hide some potential security flaws. A web server can be exploited as a launching pad into the corporation or agency's entire computer complex. Casual and untrained in security matters users or common clients for web-based services, such users are not necessarily aware of the security risks that exist and do not have the tools or the knowledge to take effective countermeasures. So this table provides a summary of the types of the security threats faced when using the web. One way to group these threats in terms of passive and active attacks. Passive attacks include an eavesdropping on the network traffic between the browser and the server and gaining access to the information on a website that is supported to be restricted. Active attacks include impersonating another user and altering messages in transit between the client and the server and altering information on the website. The typical attacks can be on the integrity, confidentiality, denial of service, and authentication of the data. So another way to classify web attacks is the web security in terms of the location of the threats: web server, web browser, and network traffic between the server and the browser. Issues of the server and browser security fall into the category of computer system security. So you can go through these threats, that how an integrity, confidentiality, denial of service, and authentication attack can be encountered, and how what are the consequences and the different ways to overcome these attacks. So a number of approaches to providing web security are possible. The various approaches that have been considered are similar in the services they provide, and to some extent the mechanism they use but differ with the respect to the protocol scope and their applicability and their relative location within the TCP/IP protocol stack. This figure illustrates the difference. One way to provide the set network security is using the IP security protocol. The advantages of IP security is that it uses the transparent to it is the transparent to the end user and applications and provides the general purpose solution. IP security includes a filtering capability that only selected traffic need to incur the overhead of the IP security processing. The second, a relatively general purpose solution is to implement the security just above the TCP layer using the SSL or TSL. The foremost example of this approach is the secure socket layer and then follow up the internet standard known as the transport layer security. At this level there are two implementation choices. Full general SSL could be provided as a part of underlying protocol suite and therefore be transparent to the applications. Alternatively, TLS can be embedded in specific packages. For example, virtually all browsers come equipped with the TLS, and most web servers have implemented this protocol. Finally, application-specific security services are embedded within the particular application. Shows the example of application level by implementing some kind of S-MIME protocol. The advantage of this approach is that the services can be tailored to the specific needs in the given applications. One of the most widely used security services is the transport layer security, and this is the current version of this transport layer security is version 1.2, and it is one of the most widely used security service. It is defined in RFC 5246. TLS is an internet-based that evolved from the commercial protocol known as Secure Socket Layer. So it is a general purpose service implemented as a set of protocols that rely on the transmission control protocol. This could be the provided as a part of the underlying protocol suite and therefore be transparent to the application. TLS can be embedded in specific packages and most browser comes equipped with the TLS and most web servers have implemented this protocol. So the TLS is designed to make the use of TCP to provide a reliable end-to-end secure service. TLS is not a single protocol, but rather two layers of protocol as illustrated in this figure. The TLS Record Protocol provides the basic security services to a various higher level protocols, in particular the HTTP Hypertext Transfer Protocol, which provides the transfer service of web client-server interaction can operate on top of the transport layer service. The three high-level protocols are defined as a part of TLS: the Handshake Protocol, the Change Cipher Specification Protocol, the Alert Protocol. These TLS-specific protocols are used in management of TLS exchanges, and it will be discussed in later slides. The fourth protocol is a heartbeat protocol, and it is defined in a separate RFC standard, which will be also discussed in next slides. So the TLS architecture has two important concepts. The TLS connection, which is a transport that provides a suitable type of service, and for TLS, such connections are peer-to-peer relationships. These connections are transient and every connection is associated with a single session. On the other hand, TLS session is an association between a client and a server. and it is created by a handshake protocol. It defines a set of cryptographic security parameters which can be shared among multiple connections. These connection sessions are used to avoid expensive negotiation of new security parameters for each connection. Between any pair of parties, applications such as HTTP and client on a server, there may be multiple secure connections. In theory, there may be also possible to have multiple sessions between parties, but this feature is not used in practice. There are a number of states associated with each session. Once a session is established, there is a current operating state for both read and write, to receive and send. The addition during the handshake protocol is the pending read and the write states are created. Upon successful conclusion the handshake protocol, the pending states become current states. So a session state is defined by the following parameters. It has a session identifier, which is an arbitrary byte sequence chosen by the server to identify an active or resumable session. It has a peer certificate, which is an X509 version 3 certificates of the peer. This element of the state may be null. It provides a compression method, the algorithm used to compress data prior to the encryption. It also has a cipher specification which specifies the bulk data encryption algorithm and a hash algorithm used for message authentication code calculation. Also defines cryptographic attributes such as the hash size. It has a master secret, which is a 48-byte secret shared between the client and the server, and a session state is resumable, which indicates a flag whether the session can be used to indicate new connections. A connection state may be defined by the following parameters: a server and a client random byte sequence that are chosen by the server and the client for each connection. The server writes the MAC secret. The secret key used in the message authentication code operations on the data sent by the server. The client writes the MAC secret, the secret key used in the message authenticate operations on the data sent by the client. The server writes the key, which is a secret encryption key for data encrypted by the server and decrypted by the client. On the other hand, client writes the key, which is a symmetric encryption key for the data encrypted by the client and it is decrypted by the server. There is an initialization vector. So when a block cipher in the CBC mode is used, an initialization vector is maintained for each key. This is a field first initialized by the TLS handshake protocol. The final ciphertext block from each record is presented for the use as the initialization vector with the following record. The sequence numbers are also maintained. Each party maintains a separate sequence number for transmitted and received messages for each connection. When a party sends or receives a changed cipher specification message, the appropriate sequence number is set to 0. The sequence number may not exceed 2 raised to the power 64 minus 1. The TLS protocol provides two services for the TLS connection: the confidentiality and the message integrity. In the confidentiality, the handshake protocol defines a shared secret key that is used for the conventional encryption of the TLS payload. In the message integrity, the handshake protocol also defines a shared key that is used to form a message authentication code. This figure illustrates the overall operation of TLS Record Protocol. The Record Protocol takes an application message to be transmitted, fragments the data into a manageable blocks, and optionally it compresses the data to a short format, then it applies a message authentication code and applies the transport layer security encryption, and then it verifies and decompresses the data to a reassemble before being delivered to the higher level user. The first step is the fragmentation, and each upper level message is fragmented into 2 raised to the power 14 bytes or less. The compression is optionally applied. Compression must be lossless and may not increase the content length by more than 1 kilobyte. In the TLS version 2, no compression algorithm is specified, so the default compression algorithm is null. The next step is the processing to compute the message authentication code over the compressed data. The TLS make use of the hashed message authentication algorithm defined in the RFC 2104. In the next step, the compressed message plus the MAC are encrypted using the symmetric encryption. Encryption may not increase the content length more than the 1 kilobyte, so that the total length may not exceed 2 raised to the power 14 plus 2 kilobytes. So for stream encryption, the compressed message plus the MAC authentication code are encrypted. Note that the MAC is computed before the encryption takes place, and the MAC is then encrypted along with the plain text for the compressed plain text. So the final step of TLS record protocol processing is to prepend a header consisting of number of the fields. These fields are referred as content type, which is 8 bits. The higher level protocols used to process the enclosed fragments are referred in this type. The major version also contains 8 bits, and it indicates the major version of TLS in use. For TLS v2, the value is 3. The minor version indicates 8 bits of the version in use. For TLS v2, it is the value of 1. The compressed length, which is 16-bit value, it is the length in bytes, the plain text fragment or the compressed fragment if the compression is used. The maximum value is 2 raised to the power 16 plus 2048 bytes. The content type has been defined, and the change cipher specification, alert, handshake, and application data. The first three values are the TLS specific protocols, which will be discussed in next slides. Note that no distinction is made among the various applications such as HTTP that might use the TLS. The content of the data created by such applications is opaque to the TLS. So the change cipher specification protocol is one of the four TLS specific protocols that use the TLS record format, and it is the simplest. The protocol consists of a single message, which consists of a single byte with the value 1. The sole purpose of this message is to cause pending state to be copied into the current state, which updates the cipher suite to be used in this connection. The next is the alert protocol, which is used to convey the TLS related alerts to peer entity. As with these other applications use the TLS, the alert messages are compressed and encrypted as specified by the current state. Each message in this protocol consists of 2 bytes. The first byte takes the value warning and the or fatal, and the second to convey the severity of the message. If the level is fatal, the TLS immediately terminates the connection. Other connections on the same session may continue, but no new connections on the session may be established. The second byte contains the code that indicates the specific alert. The most complex part of the TLS is the handshake protocol. This protocol allows the server and the client to authenticate each other and to negotiate an encryption and a MAC algorithm and cryptographic keys to be used to protect the data sent in the TLS. The handshake protocol consists of a series of messages exchanged by the client and the server, and all of these have shown the format which contains the type, which is the 1 byte indicate one of the 10 messages described in next table, and the length, which is 3 byte, the length of the message in the bytes, and the content, which is greater than 0 bytes, and the parameters are also associated with this message. So the message type can be a hello request, client hello, server hello, or a certificate, or a server key exchange, or certificate request, or a certificate verification request, or a finished value. There are other upper level protocols such as HTTP, which will be discussed in next few slides. So in cryptographic computations, two further items are of interest. The first one is the creation of a shared master key by means of the key exchange. The shared master secret is one time 48 byte value generated for this session by means of secure key exchange. The creation is in two stages. A first pre-master secret key is exchanged. A second, the master secret is calculated by both parties. The second item is the generation of cryptographic parameters from the master secret. Ciphers require a client write MAC secret, a server write a MAC secret, a client write key, and a server write key, a client write initialization vector, and a server write initialization vector, which are generated from the master secret in that order. These parameters are generated from the master secret by hashing the master secret into a sequence of secure bytes of sufficient length for all needed parameters. So in the context of computer networks, the heartbeat protocol is a periodic signal generated by hardware or software to indicate the normal operation or to synchronize other parts of the system. Heartbeat protocol is typically used to monitor the availability of a protocol entity. In the specific case of TLS, a heartbeat protocol was defined in 2012 in RFC 6250 Transport Layer Security and Datagram Transport Layer Security Heartbeat Extension. So it runs on the top of the TLS Record Protocol, and it consists of two messages types, heartbeat request and heartbeat response. A heartbeat request message can be sent at any time. So whether the request message is received, it should be answered promptly with the corresponding heartbeat message response. The heartbeat request message include a payload, length, payload, and padding fields. The corresponding heartbeat response message must include the exact copy of received payload. The padding can be random content. The heartbeat serves the heartbeat protocol is established during the handshake protocol, and it serves two purposes. First of all, it assures that the sender and the recipient are still alive, even though there may not be an activity over the underlying TCP connection for a while. Secondly, The heartbeat generates an activity across the connection during the idle period, which avoids a closure by a firewall that does not tolerate the idle connection. The requirements for the handshake of the payload was designed into the heartbeat protocol to support its use in a connectionless version of TLS known as Datagram Transport Layer. So since first introduction of SSL in 1994, the subsequent standardization of the TLS, numerous attacks have been defined uh, these protocols. The appearance of each attack is necessitated changes in the protocol, the encryption tools, or some aspects of the implementation of SSL and TLS counter these threats. So these attacks can be grouped into four categories. First is the attacks on the handshake protocol. So as early as 1998, an approach to compromising the handshake protocol based on the exploiting the formatting and the implementation of RSA encryption scheme was presented. So as countermeasures were implemented, the attack was refined and adjusted not to only thwart the countermeasures but also speed up the attack. The second kind of attack is the attacks on the record and the application data protocols. Number of vulnerabilities have been discovered in this protocol, leading the patches to the counter the new threats. So a recent example was happened in 2011. Researchers Tai Dong and Giuliano Rizzo demonstrated a proof concept called Beast browser exploit against SSL TLS that turned what had been considered only theoretical vulnerability in a practical attack. The Beast leverages a type of cryptographic attack called chosen cipher plaintext attack. The attacker mounts the attack by choosing a guess for the plaintext that is associated with the known ciphertext. The researcher developed a practical algorithm for launching successful attacks. Subsequent patches were able to thwart these attacks. The authors of the Beast attacks are also creators of 2012 compression ratio info leak made easy attack, which can allow an attacker to recover the contents of web cookies when data compression used with the TLS. The next kind of attack is the attacks on the PKI. So, which checks the validity of the X509 certificates is an activity subject to the variety of attacks both in the context of SSL and TLS elsewhere. It is commonly used library for TLS SSL suffer from the vulnerable certificates validation implementation. The authors revealed weaknesses of the open source code of OpenSSL, GNU-TLS, Apache HTTP client, URL, PHP, Python, and application built upon these products. The other attacks are that do not fit into any of the preceding categories. One example in this attack is announced in 2011 by the German hacker group The Hacker's Choice, which is a denial of service attack. This attack creates heavy processing load on the servers by overwhelming the target with the SSL TLS handshake request. Boosting system load is done by establishing new connections or using renegotiation. Assuming that the majority of the computation during the handshake is done by the server, the attack creates the more system load on the server than the source device, leading to a denial of service. The server is forced to continuously recompute the random numbers of keys. The history of attacks countermeasures for SSL and TLS is representative of the that four other internet-based protocols: a perfect protocol and a perfect protocol simple implementation strategy that are never achieved. The constant back and forth between threads and countermeasures determine the evolution of internet-based protocols. So the next is the famous the HTTP or HTTPS, which is referred as HTTP over SSL. So which implements the secure communication between a web browser and a web server. HTTPS capability is built into all modern web browsers, and it depends on the web server supporting HTTPS communication. For example, some search engines do not support HTTPS. So a user of web browser will see the URL addresses that begin with HTTPS rather than HTTP. So if the HTTPS is specified, the normal HTTP connection uses the port 80, while HTTPS port uses the port 443, which invokes the secure socket layer. When HTTPS is used, the following elements of the communications are encrypted: the URL of the requested document, the content of the document, the content of the browser forms, the cookies sent from the browser to the server and from server to the browser, and the contents of the HTTP header. The documented HTTPS in the RFC2818 and HTTP over TLS. There is no fundamental change using HTTP over either SSL or TLS, or both implementation are referred to as HTTPS. So for connection and initiation, the HTTPS, the agent acting as the HTTP client, also acts as the TLS agent. The client initiates the connection to the server on the appropriate port and then sends the TLS client hello to begin the TLS handshake. So when the TLS handshake has finished, the client may then initiate the first HTTP request. All the HTTP data is sent to be the TLS application data. So there are normal HTTP behaviors, including retained connection, should be followed. The three levels of awareness of a connection in HTTP are: at the HTTP level, an HTTP client requests a connection to an HTTP server by sending connection request to the next lowest layer. Typically, the next lower layer is TCP, but it may also be a TLS SSL. So at the level of TLS, a session established between a TLS client and a TLS server. This session can support one or more connections at any time. Finally, the TLS request is to establish a connection begins with the establishment of a TCP connection between the TCP entity and the client side and the TCP entity of the server side. So an HTTP client or server can indicate the closing of a connection by including the connection close in an HTTP record. This indicates that the connection will be closed after the record is delivered. The closure of HTTPS connection requires the TLS close the connection with the peer TLS entity on the remote side, which will involve closing of the underlying TCP connection. The TLS implementation must initiate an exchange for the closure alerts before closing a connection. A TLS implementation may, after sending a closure alert, close the connection without waiting for the peer to send its closure alert, generating an incomplete close. An unannounced TCP closure could be evidence of some sort of attacks, so the HTTPS clients should issue some sort of security warning when this occurs. So a secure shell is a protocol for secure network communication designed to be relatively simple and inexpensive to implement. The initial version of Secure Shell is SS1, was focused on providing a secure remote logon facility to replace the telnet and other remote logon schemes that not provided security. The SSH provides a more general client-server capability and can use for such network functions as a file transfer and email as well. The SSH2 fixes a number of security flaws in the original scheme, and it is documented as a proposed standard for in the IETF RFCS 4250 to 4256. And SSH client server applications are widely available for most operating systems, and it has become the method of choice for the remote login and externally. And it is rapidly becoming one of the most pervasive applications for encrypted technology outside the embedded systems. The SSH is organized as three protocols that typically run on the top of a TCP protocol. The Transport Layer Protocol provides server authentication, data confidentiality, and data integrity with the forward secrecy. For example, if a key is compromised during one session, the knowledge does not affect the security of the earlier sessions. The transport level layer may optionally provide compression. The second one is the user authentication protocol. The authentication, it provides the authentication to the user to the it provides the authentication of the user to the server, and it also has the SSH connection protocol, which multiplexes multiple logical connections communication channels over single underlying SSH connection. So in the transport layer protocol, server authentication occurs at the transport layer based on the server possessing a public-private key pair. A server may have a multiple host keys during the multiple different asymmetric encryption algorithms. Multiple hosts may share the same host key, and the server host key is used during the key exchanges to authenticate the identity of the host. For this to be possible, the client must have a prior knowledge of the server's public host key. The RFC 421 dictates two alternative trust models. The first one states that the client has a local database that associates each host name with the corresponding public host key. This method requires no centrally administered infrastructure and no third-party coordination. The downside is that the database of the name-to-key association may become burdensome to maintain. The host name to key association is certified by a trusted certification authority. The client only knows the certification authority root key and can verify the validity of all host keys certified by accepted certification authorities. This alternative eases the maintenance problem since ideally only single certification authority key needs to be securely stored on the client. On the other hand, each host key must appropriately certified by a central authority before authorization is possible. So this figure illustrates the sequence of events in the SSH transport layer protocol. First, the client establishes a TCP connection to the server. This is done via the TCP protocol, and it is not a part of the transport layer protocol. Once the connection is established, the client server exchange referred as the packet of the data in the TCP segment, and each packet is transferred in the key exchange. So the length of the packet, the format of the packet is described in this slide. The first of all, it says the length of the packet, which depends on the packets in bytes and not including the packet length of the MAC fields. There is some padding to be included which is a length of a random padding fields, and there is a payload, which is a compressed form to be included into the packet. Then there is some random padding is added. So when the encryption algorithm has been negotiated, this field is added. Then a message authentication code is embedded to create the SSH packet. So once an encryption algorithm has been negotiated, the entire packet, including the MAC field, is encrypted after the MAC value is calculated. The SSH transport layer packet exchange consists of a sequence of steps. The first step is the authentication of the string. Message begins with the client sending a packet with the identification string. The server may require one or more of the following authentication methods. The first one is the public key. This details the method depend on the public key algorithm chosen. The client sends a message back to the server that contains the client's public key with the message signed with the client's private key. So when the server receives this message, it checks whether the supplied key is acceptable for authentication, and if so, it checks whether the signature is correct. The authentication can also be done by the password, and the client sends the message containing the plain text password, which is protected by the encryption and by the transport layer protocol. It can also provide the host-based authentication method, in which the authentication is performed on the client's host rather than the client itself. This method works by having a client send to a signature created by the private key of the client host rather than directly verifying the user identity. The SSH uh, server verifies the identity of the client host. So the SSH connection protocol runs on the top of the SSH transport layer protocol, and it assumes a secure authentication connection is in the use. The secure authentication connection, referred as a tunnel, is used by the common connection protocol to multiplex a number of logical channels. The channel mechanism works as follows: that all types of communications using SSH are supported using the separate channels. Either side may open a channel, and for each channel, each side associates a unique channel number, and channels are flow controlled using a window mechanism. And no data may be sent to a channel until a message is received to indicate that the window space is available. The life of a channel progresses through the three stages: opening a channel, data transfer, and a closing the channel. When either side wishes to open a channel, it allocates a local number to channel that sends the message. Once a channel is open, the data transfer is performed. The messages in both directions may continue as long as the channel is open. So when the channel is closed, it sends a channel close message. So for four channel types are uh, recognized in SSH connection protocol specification. The first is the session, and it is the remote execution of the program. The program may be a shell, an application such as a file transfer or an email, or system command, or some built-in subsystem. So one session channel is opened, subsequent requests are used to start a remote program. The second type is the X11, which refers to the X window system, a computer software system, and a network protocol that provides a graphical user interface for networked computers. X allows applications to run over a network server but to be displayed on a desktop machine. The forwarding TCP/IP is used for remote port forwarding, and direct TCP/IP is used for the local port forwarding. So what is meant by the port forwarding is one of the most useful feature of the SSH. It provides an ability to convert any insecure TCP connection into a secure SSH connection, also referred as SSH tunneling. Incoming TCP traffic is delivered to an appropriate application on the basis of the port number A port number is an identifier of a user of a TCP. An application may employ multiple port numbers. For example, for a simple mail transfer protocol, the server generally listens to a port 25, so an incoming SMTP request uses the TCP and addresses the data destination to the port 25. TCP recognizes that this is an SMTP server and addresses the routes to the data to the SMTP server application. So this figure shows the basic concept behind the port forwarding. We have a client application that is identified by a port number X and a server application that is identified a port number Y. At some point, the client application invokes the local TCP entity and requests a connection to create to the remote port uh, at the server Y. The local TCP entity negotiates the TCP connection with the remote TCP entity such that the connection links local port X to the remote port Y. To secure this connection, SSH is configured so that the SSH transport layer protocol establishes the TCP connection between the SSH client and the server with the TCP port number A and B respectively. A secure SSH tunnel is established over the TCP connection. Traffic from the client at the port X is directed to the traffic from the client at the port X is redirected to the local SSH entity and travels through the tunnel, where remote SSH entity delivers the data to the server application on the port Y. The traffic in the other direction is similarly redirected. SSH supports two types of port forwarding, the local forwarding and the remote forwarding. Local forwarding allows the client to set up a hijacker process. This will intercept the selected application level traffic and redirect it from the unsecured TCP connection to a secured SSH tunnel. SSH is configured to listen on selected ports. SSH grabs all traffic using the selected port and sends it to the SSH tunnel. On the other hand, the SSH server sends incoming traffic to the destination port dictated by the application host. So with the remote forwarding, the user SSH client acts on the server's behalf. The client receives the traffic with a given destination port number, places the traffic on the correct port and sends it to the destination of the user chooses. A typical example of a remote forwarding is the following. You wish to access a server at a work from your home computer because the work server is behind a firewall. It will not accept an SSH request from your home computer. However, from work you can set up a SSH tunnel using a remote forwarding. This involves the following steps. First of all, from the work computer, set an SSH connection to your home computer. The firewall will allow this because it is a protected ongoing connection. Configure the SSH server to listen to your local port, say 22, and to deliver data across the SSH connection address remote port, say 2222. So you can now go to your home computer and configure the SSH to accept the traffic on the port 2222. Now you have an SSH tunnel that can be used for remote logon to your work server. That is the end of this lecture, and in this lecture we discussed about the web security consideration and threats and some ways to countermeasure these approaches. Three different uh, protocols are discussed. First was the secure software layer protocol, which involved a number of other protocols such as the SSL record protocol, the chain cipher specification protocol, the heartbeat protocol, the handshake protocol. The next protocol was the HTTPS and its connection initiation and connection closure properties are discussed. And finally, the secured shell protocol was discussed, which works on the transport layer protocol and the user authentication protocol was sketched about the communication protocols. If you want to read more about the topic, you can look at the chapter number 17 of the recommended book, or you can ask me any question. Thank you very much.